Alright, so in this section, we're going to learn how to use stoichiometry to calculate the heat associated with very specific quantities. Up until this point, we've been calculating the enthalpy of the reaction. So that's the heat associated with the generalized reaction. So if you had 4 moles of ammonia and 5 moles of oxygen, it would release negative 906 kilojoules of heat. However, what's the probability that you're going to have exactly those quantities? So we can create conversion factors from this value that will allow us to figure out the heat associated with the other quantities. So for instance, I'm going to write negative 906 kilojoules. And then in order to finish my conversion factor, I want to grab the coefficient underneath the, or next to the ammonia. So there'd be 4 moles of ammonia associated with negative 906 kilojoules. Like all conversion factors, we can flip it. So we could say 4 moles of ammonia in the numerator and negative 906 kilojoules in the denominator. It doesn't have to be ammonia. You can set up this conversion factor with any of the reactants or products. So for instance, you could say, oh, if I had 6 moles of water, I would expect negative 906 kilojoules. If I had 6 moles of water produced, I would expect negative 906 kilojoules of heat to be released. That could be flipped. You can use the oxygen, you can use the nitrous oxide. So whatever combination suits your end goal. Alrighty, so in number 14, we're given the fact that we have 155 grams of ammonia. So we'll start with that. We want to get rid of grams of ammonia, so we'll divide that by the molar mass. So there's 17.03 grams of ammonia in 1 mole of ammonia. Grams will cancel grams. Now, in order to get rid of moles of ammonia and convert that to heat energy, I'm going to grab this coefficient right there. So 4 moles of ammonia will produce negative 906 kilojoules of energy. Now moles are gone, and we're just left with units of kilojoules. And the answer here is going to be 2.06 times 10 to the 3rd kilojoules. And we do have a negative sign. It's an exothermic reaction. Alrighty, so in problem number 15, we see the classic combustion reaction. The fuel here is propane. And we're told that someone's having a barbecue and they burnt 13.2 kilograms of propane. We're asked to calculate the amount of heat energy produced by burning this 13.2 kilograms. First step is to convert the kilograms to grams. So there's 1,000 grams of propane in 1 kilogram of propane. After that, we're going to use the molar mass of propane to turn it into moles. Finally, now that we're in moles, we can grab the coefficient of the balance equation. And so here I'm going to use that 1 mole of propane. And after we grab the coefficient, we can relate that back to the enthalpy value that we were given. So in the numerator, I'm going to put negative 2,044 kilojoules. Let's see how everything's canceling. So kilograms will cancel kilograms, grams with grams, moles with moles. And we have a negative value, makes sense. we're burning something, it's highly exothermic. And our answer here is going to be negative 6.12 times 10 to the 5th kilojoules. Alrighty, so number 16 is a tiny bit different in that we're starting with the amount of heat. So they gave us the fact that 1.5 times 10 to the 3rd kilojoules of heat was produced. The word produce is really critical here because when we think about something producing heat, like a combustion reaction, some type of fire, we think of exothermic reaction. So produce implies exothermic, which means we need to put a negative sign on this value before we get started. I want to get rid of kilojoules, so I'm going to grab the delta H value, negative 2,658 kilojoules. And they're asking us how much butane we need. So there's 1 mole of butane in the balanced equation. And they want that value in grams. So kilojoules cancel kilojoules. And now I'm going to use the molar mass of butane, which is 58.14 grams. And I'll be left with the grams of butane, which is 32.8. The next part of the problem asks us to predict how much carbon dioxide will be produced when we make the 1.5 times 10 to the 3rd kilojoules of heat. So let me start with the same value again. I'm going to grab that same delta H value, except this time in my numerator, I'm going to put 4 moles of carbon dioxide. I want to get rid of the moles of carbon dioxide. Put my molar mass of carbon dioxide. Just check how everything cancels. Moles cancel moles and kilojoules are kilojoules. And so I'm just left with grams of carbon dioxide. So when I solve this way, I got 99.3 grams of carbon dioxide. A lot of times when I do this problem in lecture, students will say, well, can I use this value here? Absolutely. And this kind of proves what I was discussing before about state functions. It doesn't matter how we approach the problem. So another option to that second part of the problem would have been to grab the 32.8 grams of butane, convert the grams of butane to moles of butane. We have the molar mass. And then using the mole to mole ratios from the balanced equation, so I'm going to use the 1 and the 4. I can turn the butane into carbon dioxide. So 1 mole of butane is associated with 4 moles of carbon dioxide. And then the last step here would be to use the molar mass of the carbon dioxide to get it into grams. And when I plugged this all in my calculator, I got the same answer as before, the 99.3 grams of carbon dioxide. So it really doesn't matter how you set this problem up or how you go about solving it. You should get the correct answer regardless of your approach.